Hi everyone, thank you for being here. I'm Alberto Modesti, and under the supervision of Eduardo Aedo, Jiewei Zhou, and Filippo Cioschi, I'm working on my thesis with title A Three-Dimensional Model and Simulator of Energetic Plumes from Space Plasma Thruster. I'll recall a bit the logical frame of my thesis, starting from the gaps in literature that provides the thesis motivation. So there's a lot of interest in assessing the 3D plume expansion effects with physical insight on the expansion of the plume in terms of the magnetized electrons' behavior. Also, we lack of some knowledge of what's happening when the physical scenario involves electrical connection or more complex object interaction with the plasma plume. And of course, the final goal of the thesis will be to assess the difference between the free space scenario, which is something that experiments struggle to achieve in short times, and ground facility conditions, which is the experimental actual conditions. The code chosen for fill these gaps or provide more physical insights is called EP2+, which is a 3D hybrid particle inside himself fluid simulator. And the objectives of the thesis, so the main tasks I have to tackle, are related to the code upgrade, which can be numerical or physical, and the code application and validation of the models implemented in order to finally apply the code in the different scenarios chosen. The common methodology and logic behind the thesis, which is transversal to all the tasks I'm supposed to tackle, are that all the improvements have to be independent, but with an holistic view, so taking into account all the other code's capabilities. Then there's the intention to make the code easily interfaceable with other codes of the research group, and also to use these other codes to validate the models implemented, or in any case, this new implementation have to be tested and validated with the previous models, if any. Then, in order to apply and challenge the code, in different scenarios, we are collaborating with and supporting several projects, so involving more universities and companies from the simulation and from the experimental point of view. EP2+, or better EP2+2, which is the upgraded version I'm gonna provide, let's say. It's a 3D hybrid particle in self-fluid code, as I said, that models the heavy species, so the neutrons and ions, with a particle in cell approach, so dealing with their motion, collisions, or sorting of the particles. Then there's a module of the code responsible for the object interaction, so dealing with the interaction with the walls and providing the boundary conditions for the plasma at all the boundaries of the domain for the fluid equations. And in addition, solving the electrical part of the model. The fluid equation regards the electron population, and the model we want to validate involves the continuity equation, the momentum equation, energy balance, and heat flux closure, which reduces to a simple Fourier law in our case. And eventually, we want to add make functional in the scenarios of interest. So in a non-neutral regime, we solve also the Poisson equation. As a summary of my first and second year achievements, there's the implementation of, from the numerical point of view, the implementation of the new finite volume scheme for the discretization and solution of the electron equations, which has been compared also to the previous finite difference schemes and assessing its advantages. Then, in order to apply this scheme to all the possible scenarios of the code to make it flexible, we improved the boundary conditions and validated in scenarios such as the gridded ion thruster with the 3D spacecraft body, then magnetic nozzle simulation scenario, and Hall effect thruster plume scenario. Also, a more complex scenario, which is the last one, is the design and setup in terms of inputs and models and domain shape of ground facility conditions, in which we tested with all the polytropic models, so simple electron closure, a 5 kilowatt thruster plume in its ground facility. Then, from the point of view of the model improvements, we started the implementation and the formulation and implementation with the new finite volume scheme of the energy balance and heat flux equation in order to overcome the limitations due to the polytropic closure. Now I start presenting the third year works. So here I recall the first year / second works on the validation of the finite volume Cartesian staggered discretization scheme. We compared it and validated against the previous finite difference scheme. And during this process, well, of course, the comparison was successful because at medium high resolution, the two schemes coincide. And while at low resolution and high magnetization, relatively high, the finite volume gives a smoother solution. So we assessed some advantages of this new model, but in the meanwhile, we got interested in the weaknesses of the finite difference scheme. Because in this scheme, it's not conservative in terms of truncation error associated to the finite differences discretization, that in this kind of equation, that I'm going to show you in the next slide, appears as an artificial source of electric current. This perturbs the actual physical solution of the equations, and a higher resolution is required to mitigate this effect. The second order finite difference scheme error origin assessment, which is an issue that we want to get more insight into in our journal paper that we want to publish soon, has to do with the form of the equation we discretize. Because in this finite difference scheme, which is second order, we substitute the momentum equation into continuity one. We obtain the second order elliptic equation, which is going to be discretized with a second order finite difference scheme. And we were interested in find the origin, the sources in terms of which part of the equation affects this error that rises in the solution. And after analyzing simplified scenario and perform simulation with simple hypotheses, we could isolate the main sources of this error in terms of the discretization of the right-hand side term, which involves the divergence operator, and in the boundary condition application of this kind of problem, which involves a directional derivative imposition. In finite difference discretization, these operators are affected by a truncation error, and we could isolate these terms as responsible of this error. Another kind of numerical error is associated to the frame, so reference in which we discretize the equations. For example, in the hyphen code, uses which is also axisymmetric, uses a magnetically field aligned mesh, which is a principal frame with respect to the physics of the problem, while EP2+ employs a Cartesian mesh. When you discretize the Ohm's law, so the momentum equations, in the magnetic principal frame, you just have that every component of the current is a result of one main contributor of order of magnitude bigger than the other terms. While when you discretize the equations in a Cartesian frame, you have that each component is among the other terms, there are at least two terms of opposite sign, which are of order of magnitude higher than the actual solution or of their difference. So you have the subtraction of two terms, at least of a high magnitude, which have an uncertainty comparable to the magnitude of their difference. This phenomenon is numerically called catastrophic cancellation. We also associate it to numerical diffusion, and here is a visual representation. And in some locally, in some zones of the domain, we have that the solution is the subtraction of these two big magnitude quantities. And typically, this problem is solved by adopting some numerical strategy to put the terms to a lower order of magnitude, or to change the reference frame, which we cannot do if we work in a structured mesh, or refining the mesh. So for now, we focus on the mesh improving in order to increase the resolution, since this method is the only reliable one that works every time. So the mesh refinement solves the problem. The limits are the magnetization level, defined by the Hall parameter, that require a higher resolution, or a complex configuration, such as the facility conditions, bigger domain, in which you have already a large number of nodes in 3D. So there are limits to the high resolution achievable, but we are sure that increasing the resolution gives less noisy and with profiles and with less peaks, and that makes the solution smoother and nicer. In order to improve a little the mesh in terms of resolution, we develop a highly non-uniform mesh algorithm that for now makes us mitigate a little the increasing number of nodes of the simulation. To balance this, we also changed the Fortran compiler from G-Fortran to Intel with MKL PARD, so direct solver for the system. This allowed us to improve by a factor of 5 the times required for the solution of mainly the fluid part of the simulation, and allowing for a simulation speed up. Then from the point of view of the application and the validation of the models, we chose 3 scenarios that we are going to tackle, which is the free space electrode plasma thruster expansion, free space Hall effect thruster plume expansion, and ground facility expansion of Hall effect thruster also, which is more complex and involves coupling of the model with ancillary models for the complexity of the domain. All the injection profiles at the exit of the thruster are taken from Eiffen simulation. The first successful comparison between the codes for the validation of the new model is in this electrode-less thruster plume scenario. We start by comparing with the 2D Eiffen code, and these are the first results. When we compare the 1D axial profiles for several magnitudes, such as density, temperature, heat flux, and electric current, we see a pretty good match of the profiles. Then if we move
Alberto,
to the...
you need to finish.
Yes, like the last ones. Then if we move to the Hall effect thruster plume in free space, we are still in work in process to match with the Eiffen results, because quantitatively we still don't have a good agreement, because of we are investigating something associated to the boundary condition or the plume models, but we have some stable converged solution already. The next tasks of my 4th PhD year would be the publication of papers and last project's deliverables, and the thesis writing, which have a lot of contents in common, of course, and to complete the validation of energy equation, assess 3D effects and the facility effects in the last scenario I described. I also plan to do a research stay with insight on plasma wall interaction probably, and this is a summary of my first and second achievement, scientific production, and the third year ones. And that's all from my side. If you have any questions, I'm here.